Well, thank you, Dr. Bell. They say that as you get older, you develop a sort of rapport with all living and inanimate objects even. And I guess it's true because listening to the talk here, I was thinking of some of the old fallen down buildings that I've seen, and I know just how they feel when they're denominated historical monuments. With that bit of rapport with the history, I'd like to make a few remarks. In the first place, I'll say a few things that you all know about. In fact, most of what I say you will know about, but I'm saying them because I want to put it into perspective of the time nearly 40 years ago when we were first thinking about things of that sort. Now, of course, as you know, the history of computers in the sense of devices to aid computation goes back thousands of years to the counting pebbles and marks on clay tablets, and even the abacus, which may still be, for all I know, the most widely used calculating device today, is a couple of thousand years old. More recent devices, recognizable as desk calculators of a primitive kind, were built by Leibniz and Pascal, and there's some reproductions of these devices, or one of the devices in your museum, which I thought was very interesting. This was approximately 300 years ago, and then following that we have Charles Babbage's engines with their extremely modern concepts, which were designed and partially built with the technology of their time, which was about 150 years ago. So we're gradually approaching the present time. Babbage borrowed the idea of data storage or information storage in punch cards from Jacquard and his loom, and then 60 years later, Hollerith at the Bureau of Census borrowed the punch card to store statistical information, and he combined them with mechanical adders. Then another half century passed, and several independent computational projects took form simultaneously. Now, quite unfairly, I'm going to omit reference to some highly original and potentially influential developments in Ireland, Spain, France, and elsewhere prior to that time, and talk about just one of those developments, namely the one that I know from firsthand experience. Now, I've said that these developments were potentially influential because, in fact, there was little effective communication among the computer pioneers, and each development, with possibly one exception, I think, took off from very ancient beginnings, or at most from the Hollerith cards and Pascal's mechanical computers. Now, the period that I wanted to talk about myself ranges from about 1935 to 1945. And in that time, there were 4 independent developments, at least, ones that stand out, at least in my recognition. In Germany, at some time during that period, which the date not being too clear, Konrad Zuse made a computer using a mechanical relay. The military secrecy was such that it was a long time before we in this country have even heard of the device. I have never been entirely clear about the dates on which Zuse made his developments. He later did develop an electrical relay and a computer based on that. Meanwhile, and overlapping the same development, at Iowa, Atanasov made a simple electronic device with mechanically refreshed capacity memories. Then I made a calculator out of telephone relays at the Bell Laboratories, and Howard Aiken at Harvard began to work on a mechanical calculator using IBM parts. Now, these developments were almost entirely isolated from each other, partly by accident, and partly by military security, and partly by commercial caution. Only one of them relied very heavily on the earlier work. That was Howard Aiken, who had studied Babbage thoroughly and adapted the IBM's adaptation of Hollerith's machine to those concepts which Babbage had laid out many years before. The result was Mark I, which was the last of the large computers to use trains of gears and shafts to perform calculations. It was decidedly a large-scale mechanical device, and I have a vivid recollection of the 40-foot-long shaft whose diameter appeared to be about, as my recollection, something like 18 inches or so of steel running from one end of the frame to the other, designed to synchronize the accumulators on the two ends of the frame. Now, to the best of my knowledge, all four of these projects overlapped in time. Now, exact dates are a little hard to come by, and I don't claim to be a competent historian in any sense. And furthermore, I was invited here to talk about my personal experiences and recollections, and for this reason, I do not advise that you take my historical information too seriously. I feel a little bit under the cloud that Mark Twain shed on one of his colleagues when he said that the man was an extremely good historian in instances where facts were of no consequence. So don't worry too much about the facts. I will try to convey the flavor of the time. And in many cases, I have borrowed dates from my former colleague, Ernest G. Andrews, who collaborated with some of the very first of the computers, and whom I hoped would be here today, but I couldn't quite persuade him to leave Hanover. Now, the ancient chicken and egg priority argument, which you recall, who came first, the chicken or the egg, it seems as popular as ever today, but now it's turned to science history. And the question is, are creations due to popular demands, or are the practical application the result of the abstract creative effort? I can't say in general what the answer is, but I can tell you that in the case of the relay computers that I had a hand in, the initiation was entirely a matter of curiosity about the way in which relay circuits could be combined and activated. It was just a curiosity about the logical properties of the contacts, which individually seemed so extremely simple, and in collective masses could do some very remarkable things in the telephone business. As I say, this had no connection at all with the need for computers at that particular time. Now, as a mathematical engineer at the Bell Laboratories, everybody was an engineer then of some sort, or else a girl. And as the engineer part, I was asked to take a look at the magnetic behavior of telephone relays, which, as you probably recognize, were very important devices in the telephone system. And I became interested then in the contacts rather than in the magnetic circuits. I did play around with the magnetic circuits and try to systematize the design a little bit in that area. But I noticed that the relay contact is a binary device. Now, the binary devices are familiar. They're like the light switches in your home. And if you'll pardon my pointing out these things, it is simply because at the time that I'm discussing it, they were not so common and not so firmly recognized as they are today. The light switch and the relay contact had only two stable conditions, off and on, And this, I realized, was true of the digits in binary notation. Now, nowadays, the binary notation is familiar to most youngsters, and it's hard to realize that in 1937, that I, with a PhD in applied mathematics, had to stop and think back considerably to decide what a binary notation was. I had a vague idea. On looking it up, it became familiar to me again. And we decided to try it out as a means of using the telephone relays. And so late in November of 1937, I borrowed from the lab's scrap pile a couple of U-type relays. These relays that you see here are the U-type relay, and I assembled them in a configuration as nearly like this as I can remember. This thing has been reconstructed and is only a few months old, but I think it is almost exactly what the old relay computer was. And we have here a couple of contacts made out of sheet metal cut from a tobacco can. These are relays that were salvaged from the scrap pile. A couple of light bulbs, which are the output for the adder, and it's designed to add two one-bit numbers. Here's A and here's B. If B is 1, the sum is 1. If A is 1, B is 0, the sum is 1. If A and B are both 1, we get a 1 and a carry and a 0 in the first bit. So this device was rather amusing, and I took it down to the Bell Laboratories, having made it at home, as I said. Took it to the Bell Labs and showed to some of my friends down there, and they were satisfactorily amused by the idea that you could use binary notation from the old days to do arithmetic in the modern times. Well, then, I wasn't entirely sure that it was so funny, so I started to think about the possibility of doing a little more elaborate arithmetic than 1 plus 1, and I drew up some circuits at home for a calculator that would be something like a desktop calculator. Now, so far, this was just curiosity that was guiding the development. Slightly later, the other protagonist in the argument about chicken and eggs appeared, namely the need for a calculator. Now, I'll point out as a background that the early days of the 20th century were characterized by a development in mathematical form of the theory of communications engineering. The basic principles of this field were expressed in terms of complex numbers because they represent nicely the characteristics of alternating currents that both the power industry and the communications industry use. As a consequence, a great deal of complex number arithmetic was performed at the Bell Laboratories. In our group, which was a mathematical research group, we had 12 girls, if you don't mind the expression, which it was a term that was used at that time, who did nothing but calculate with complex numbers using desk calculators. Now, there are ways of getting complex arithmetic rather easily if you don't need precision, but we needed 8-place precision in most of the results, and so the desk calculator was the device that was used. If you've tried it, you know that the arithmetic of complex numbers, when it's been converted to multiple operations with real numbers and carried out on desk calculators, is even more tedious and subject to errors than bookkeeping. And with my experience with the checkbook, I know that's rather disagreeable. And furthermore, in the late 1930s, the computing load was increasing rapidly. More and more filters and networks and so on were being designed in the laboratories. Well, now, early in 1938, this was a year shortly following the time when I was playing with this device, Nelson Sowers, one of the operating company employees, suggested that 2 desk calculators might be fastened together mechanically somehow to do the work of the complex arithmetic. That plan was circulated around the laboratories, and my then supervisor, Dr. Fry, showed it to me and asked whether I had any ideas. Well, naturally, I'd been thinking about the relay as a device for doing arithmetic, and it's well known that you can easily connect electrical circuits with a soldering iron. You don't have to do a lot of mechanical design to get them to work together. And so I proposed that maybe the relay circuits could be used to do the complex arithmetic. So I sketched up some circuits for a complex number calculator using standard telephone relays, which were remarkably reliable, teletypewriters and other devices of the sort that were in general use. Then the schematic was turned over to Sam Williams, who was a relay circuit designer, for his opinion on the practicality and cost of building the gadget that I had suggested. And Sam, after struggling quite a bit with my rather unorthodox drafting procedures, decided that probably the thing could be made to work. And he made several useful changes, substituting, for instance, the crossbar switch, which was then a new device for numerous relays that I had used as storage devices. And he suggested this U-type relay, again, the type that I have here, as the principal device for the machine. The U-type relay was then known to have a remarkable failure rate of about 10 to the minus 11th per contact operation. That's a large number. So the project was started in September 1938, and construction began in June 1939. The design work, assignment of relay types, fusing, and all the multitude of details that have to be considered were taken care of by Sam Williams. Now, I had promptly, when I started to think about it, decided against training operators to use the binary notation. But I had considered the alternatives of converting all numbers into binary form inside the computer, or converting decimal digits into binary form at the keys. Now, because of the large amount of input and output we expected from this device, we decided on the latter. That is, each key would convert its own decimal digit into binary form. And what I had then was a binary coded decimal notation, which allowed us to use the binary adders that I'd devised. There were other coding schemes used in the Bell system, but none of them seemed to be suitable for arithmetic work. There was a slight change to be introduced in the representation of decimal digits in binary form, at least we felt so at the time, and that was that in the use of the binary adders, we ran into considerable complication when we wanted to carry from one decimal column to another. So it occurred to me that there are some nice properties of other forms of binary representation. I decided to shift all the digits by 3 units. In other words, decimal zero is to be represented by what we would normally call a binary 3, and so on up the line. Well, the nice thing about that is if you add on binary adders 2 numbers which are expressed in this code, a binary carry occurs at just the right time, namely when the sum reaches 10. And it has another nice feature that it's symmetric, and if you invert the batteries that operate the relays, you get the negative of the number that you started with, and that also was useful. Well, this we called a shifted or XS3 code, and it was used in several of our computers. About 20 years later, it was advertised as a UNIVAC code, but that has since been retracted, I think. Well, now this device was, and we'd like the first slide, if you please. We can see a sketch, and I'm sorry, no, it's the one with the, first one's the one with the circuit line on it. I guess I've got to turn this side. No, not that. No, sorry. Sorry. Thank you. Sorry about that. This is a, see the date somewhere there, 1938, and it represents a binary adder using the relays of the sort we have here. And it was one of the first attempts to make use of the binary notation. Well, now, having started that way and having been corrected in some instances by Sam Williams, we finally got the circuitry all together. And in about the middle of 1939, we had the system working. The next slide will show the frame, I hope, with the relays. No, that's the last one. That's the next to the last. There we are, good. That is the working part of the complex number calculator. These are the crossbar switches I mentioned. They're really multiple relays. The other stuff over there is practically all relays. This, as I recall, is the arithmetic part, and up there are the memories. The device cross-multiplied and multiplied two. In multiplication, you multiply the real and imaginary part of one number by the real part of the other, and those were carried out simultaneously to save time. This was very fast, a very fast machine. It took only about 30 seconds to perform a complex division. With the girls on their desk calculators, that would have taken 3 or 4 minutes at least, and would involve something like 6 transfers of numbers from paper to keyboard and back again. And so it did seem to be worthwhile. The calculator worked quite nicely for the early months of 1940, and it was decided that when a meeting of the Mathematical Society was announced for September, that we would demonstrate the machine and give a paper on the subject about why it was useful and how it worked. The original idea was that we would have a telephone line open between Hanover, where the meeting was to be held, and New York, where the machine was, and someone at the meeting would call to the operator on the phone down in New York and ask her to put numbers in the computer and report back what it said. And this scheme was very shortly modified so that the computer would respond directly to a teletype which was located in Hanover and would send data back to that same teletype. Would you please give us the one with the sample numerical list? That's it, good. This is a photograph of one of the very early, I think this makes me think that was probably 1939 when the debugging had not been complete and we were still working on trying to get numbers out instead of yammering. The rest of it went nicely, so I assume the correction was successful. As you notice, the operator, these are 8-digit numbers, the operator would introduce the real and imaginary parts with a little new character, plus I or a plus minus I as a separate character, and the multiplication sign. This is of little interest. The division, you notice, is the wrong way around, and that is not a mistake. It turns out that if you know the divisor immediately, you can start squaring and adding. And so that saved a certain amount of time. The divisor went in first and then the dividend, and it saved a matter of seconds. quite a few seconds, as a matter of fact. Well, we had our meeting in New York, and everything went all right. We had the typewriter set up in the back of the room. After the lecture, the audience was invited to put in problems. Norbert Wiener was one of the people there. He tried to get the machine to divide by 0 and was told that by the machine that this was no good. I've forgotten what it said, NO, I believe, or some such thing. And the other, John Mockley, was also there, and he tried his hand at it. So we had two people who later became pretty well known in the field of calculation, of calculators and computers. I think the Dartmouth demonstration was the first long-distance control of a computer. And we had another first for the complex number calculator, and that was that since there were several groups who were interested in using it, we installed 3 teletypes in different parts of the building, and 3 operators could use it on the assumption that the one who got there first was the one who was served first, and the others had to wait. So it was not time sharing in the modern sense, but at least it was a sharing of the facilities among various people. Now, while this Model 1, incidentally, the calculator continued to work at the Bell Laboratories for about 10 years and was finally cannibalized in 1949. So there's nothing left of it anymore except the ghost of an idea. Now, while Model 1 was being built, I began to think about other and more elaborate computers and other things that could be done with the relays. In particular, I thought it might be nice to have a calculator that would evaluate mathematical functions, say polynomials or rational functions, some such class of functions. And so I started building on paper to design a calculator of this sort. And that suggested that if we were going to have a device that would do a lot of things of this sort, it would be well to have the program written down in a form such that the operator did not have to sit and punch keys. And so it was proposed in one of the drawings that we have a teletype paper punch, and use punch paper tape to hold a program. That particular scheme was not actually put into practice for 2 or 3 more years, but then it became rather useful. Furthermore, there were other difficulties that came to mind. And as I say, these things are so obvious now that it seems a little silly to talk about them. But at the time, it was a puzzler. We were thinking of long sequences of operations controlled by a punch paper tape, and wondered where we would put the decimal point. Well, if you were doing 2 or 3 multiplications, it's quite easy to look ahead and see where you want the decimal point put, and you slide decimal points around and correct for them when you get through. But if you're going to have 20 or 30 operations, you don't know what the magnitudes are going to be. And so in a memorandum of 1940, I proposed that the computer be caused to do its own corrections for orders of magnitude. And one of the sketches that I had shows a computer in which all the numbers are introduced as proper fractions, not as 1 plus, not as 1 point, but as a number, a real proper fraction, multiplied by a power of 10. And the computer had a little, on paper again, had a little additional adding device on it which took care of the changing of the powers of 10 when you performed a multiplication. Now, none of these machines was built for a very good and practical reason. Model 1, the complex calculator, was then studied by the group at the Bell Laboratories, and everyone was horrified to find that it had cost $20,000, including the development, design, construction, and debugging. Well, this is a number that simply wasn't thinkable. The idea that anybody should spend $20,000 for a mere calculator was something that was not acceptable, and the labs decided that no more things of this sort would be built. But about then the war broke out, and the demand for computation grew tremendously, and furthermore, it grew to such an extent that we were unable to train people to do the calculations that were required for military purposes. So we decided to start out on a small scale and build a little computer which we called Model 2, or the relay interpolator. That took care of a very limited kind of activity. It happened that I was taken over for the duration of the war by the Office of Scientific Research and Development, and in particular the group that was working on fire control equipment, that is gun predictions. The prediction is no good in a static situation, and so if you want to test a device of that sort, you have to do it in motion. About that time, a device called the dynamic tester had been developed, in which the very accurate cams were slowly rotated, and data was introduced into the system by cutting the proper radius of the cam at each of its angles, and it rotated once during the course of a simulated target. Well, the cutting of cams is a very expensive bit of work and requires equipment that could very poorly be diverted from other kinds of activities. And so it occurred to me that maybe we could use punch paper tape here. We set up a little sampling servo working from punch paper tape. And then we found out that it was going to be a tremendous job. Well, we knew it in advance. We found out that it would be a very tedious job to do the calculations of the data that had to go into the punch paper tape. And so it was proposed that we build a little calculator to do the work for us. And that was one of the first devices, I think, that actually used punch paper tape stored programs. The device was built, it had about 400 and some relays, quite a simple gadget. It used teletype inputs and teletype punches to produce the paper tape that was going into the dynamic tester. And all in all, it turned out to be quite satisfactory. It was run normally almost 24 hours a day and 6 or 7 days a week. The girls would load it up, the operators, I should say now, the operators would load it with punch paper tapes made into loops so that the program was repeated over and over again on new data. The new data was brought in from punch paper tape, and the whole operation proceeded automatically. Normally it would be loaded up Friday afternoon, and Monday morning we'd come in and find a wastebasket full of punch paper tape ready for the dynamic tester. That gave us a chance to use a new idea which had been developed in the meantime, so I'd been thinking of for some time, because we had experienced some trouble in the complex number calculator of relays sticking or operating slowly and upsetting the whole calculation. The complex number machine had, say, a bank of relays which were going to perform an addition. Another relay would turn them on, cause the selection to operate, and when the proper time had been allotted, the relay would release and let the counting relays fall back. But that means that we have to allow enough time for the very slowest relay that was ever built of that particular type, and that slowed the machine down. Furthermore, if a wire broke or if a relay stuck, our answers would be wrong. And that was rather serious. And so our next trick was to devise a different algebraic scheme, a different notation for numbers. And the thing we devised was called a biquinary notation. If we can get the next slide, we have a picture of some circuit drawings showing the quinary part of the biquinary adder. The interesting thing about it was that we were able with it to, no, it has a circuit drawings on it, a lot of little lines, scratchy lines going in all directions. The interesting thing was that with that particular note, no, I'm sorry, not yet. I'm going to try again. There's another circuitry. The interesting thing was that we could, with this biquinary notation, perform a checking operation, and we set up the first, I think, of the error detecting codes, and we could use the error detecting codes also as a self-timer. The result was that we had a device in our Model 2 which was essentially foolproof in the sense that any single error occurring anywhere in the system, a broken wire, stuck contact or whatnot, would cause the machine to stop and wait until it was corrected. One of our favorite tricks was to go in while the machine was busy grinding away data, stick a toothpick into one of the relays. When the machine needed that relay, it simply stopped and waited, and you pulled the toothpick out and it went ahead and gave you the right answer anyway. I don't think there were any errors that were ever traced to the computer itself. The other equipment was somewhat less reliable. I think skip that one, I guess. You see one with two girls sitting at a desk? Good. This was the next relay calculator. Since the other machine worked, the relay interpolator worked quite well, it was decided that perhaps we could do something more elaborate. And the anti-aircraft artillery board needed a lot of ballistic calculations. So we used the biquinary code, set up a calculator, largely a detail designed by Mr. Andrews and his group. And this is the way in which data would enter the machine. It's a slight bit of historical interest in the young lady on the left who was then in high school and is now one of the leading members of the IEEE various committees and pretty high power executive in the New York Telephone Company. You can see that it's largely a teletype equipment. Mr. Andrews introduced something that has been of great use to us since from the telephone business, and that's a self-diagnosing system. Not in this particular picture, but on one of the relay racks, there are a number of diagnostic circuits, indicators which show what's gone wrong if it has, and about where the trouble occurs. Well, this machine had about 1,500 relays. It worked quite well at the anti-aircraft artillery board, and the Navy the Naval Research asked for a duplicate, which was added. Andrews himself designed in equipment which would allow it to operate on a shipboard model, which has, as you know, a lot of rock and roll and yaw and so on, and for which we needed very, very frequent references to sine and cosine tables. Now, our original device, the one that's shown here, had tables in it for ballistics on punch tape, but they were relatively slow. It didn't matter so much here because you looked up a bit of ballistics tables, and while the machine was looking for that, it could go ahead with some other calculations, and when the other part got through, the part of the calculation that got there first waited for the other one. But when the Navy wanted to use it for sines and cosines, then the delays were a little more important. And so Andrews added a permanent sine and cosine table on relays. That's a ROM circuit. Now that one worked for quite a while. Incidentally, I forgot to mention that Model 2 lasted for about 18 years, counting its stay at the Naval Research Lab. This Model 3, which we have here, ran for a considerable time. It was intended to run night and day, and consequently, it put a strain on the operators because it's very easy for somebody to put in a ridiculous symbol into a punch tape, and that would stop the machine, and it might lose a whole night's work. Therefore, when we got the machine going, a small addition was made in which one of the relays, in the case of a failure lasting for more than, I think it's 5 seconds, would close, and that closed the circuit, which rang a bell over Sergeant Stoddard's bunk, and the sergeant was expected to get up and fix it. So that. Now the last of the relays, Model 4, incidentally, this was Model 3. Model 4 was the Navy version, which was identical, as I say, except for the sines and cosines. The last of the series was, with which I had any contact, was Model 5. The work at the Aberdeen Proving Ground had by that time become bogged down because of the necessary calculations. Enormous amounts of calculation were required. And so with the assistance of the number of the military people in at the Proving Ground and the Bell Laboratories, we set up and outlined a much more elaborate computer, which was finally built and became Model 5. This was a giant of computers for those days. It had something over 9,000 relays. There were 2 complete central processing units which could be coupled to operate on a single problem or could be divided into 2 to work on separate problems. It had 6 input centers. At each center there would be a teletype, a keyboard, input punch readers, punch paper tape readers, typewriters, punches, and all of that sort of equipment with a number of loops for program tapes. As I say, there were 6 of these individual units, and they were arranged in such a way that there was a priority assigned to each one. The computer at night would be started off, say, on center number 3. It would work on that. If it finished, it would go to the next place in priority, not to number 4, but to the center having the next higher priority. If the machine made an error and stopped for any reason and did nothing for a matter of a few minutes, then that problem was dropped and the machine went on to the next center in priority. That computer used the floating decimal point for the first time, I think. At least that's the first use of it that we've been able to find. It also had a logic calculator joined to it, which would calculate the conditions under which various kinds of actions should occur. It had a jump instruction. The jump was not as convenient as the modern computer is because at $10 a bit, we did not store programs in the computer, in the working part of the computer. We started on punch tape. But if we were starting, for example, a solution of a differential equation, we'd need one routine to set up the terminal conditions, the end conditions, or the beginning conditions, another routine for the main running part, and the computer was set up so that it could jump from one to the other as it required. if the steps in the computation, in the solution of the differential equations became too long, it automatically pulled in another routine which shortened up the step and recalculated the conditions under which the new part of the solution should occur, and vice versa. If the steps became too short, it did the other way around. So it had a rather large number of possible applications and modes of operation. As I say, they had something over 9,000 relays. The last picture will show a general view, a view of part of the computer. It occupied a space approximately like this room and consisted of many banks of relays, teletype. You can see bits of the teletype equipment. They had 55 pieces of teletype equipment, including punches, tapes, this, that, and the other thing. Oh, I'm sorry, I can't see it from here, so I'll take your word for it. Is that better? That's around 2 minutes. Oh, there we are. All right, there we are. That looks a little better. Well, this poor machine was retired. The operator, who was really an expert in writing a machine language, and of course these computers all used sort of a machine language with some abbreviations and so on. And our Miss Mason Cup from the ballistic proving ground was heartbroken when the machine was finally retired in favor of the ENIAC, which came along about that time. For a considerable period of time, this machine out-computed the ENIAC. There were many weeks during which it ran within 1 hour of the entire week, except for routine maintenance, which was done on small parts of the machine at a time. So 147 hours of computation in a week was not at all unusual. And since the ENIAC at that time was computing about 15 seconds out of an hour or two, we could keep up with it in spite of the ENIAC's high speed. Well, those are the things that I remember from that period. I hope that I haven't, again quoting Mark Twain, who said that his trouble was not, as he grew older, that he forgot the things that happened, but that he remembered the things that didn't. I hope I haven't introduced things that didn't happen, and thank you very much. I think the young ladies are just going to pass the microphone around in spite of their rather warlike appearance. Oh, that's nice. A couple of the computers had sad histories because the one that was loaned was to be given from by the Anti-Aircraft Board to, I think it was somewhere in the Middle West, a university, was being shipped out on a truck, and the truck ran off the edge of the road. The whole thing smashed into small pieces. Another one was being sent to India, I understand, and fell off the deck and is somewhere in the Indian Ocean.
Did you and your colleagues discover the applicability of Boolean algebra?
Yes, it was a little complicated. The very first machine, I don't think we really thought in terms of Boolean algebra. For the second one, we began to think in terms of Boolean algebra and use it a little bit. And that was about the time that Claude Shannon's thesis from MIT appeared in the Bell Labs. And so we got a good dosage of Boolean algebra from that. And we did use it. I'm down on their books as a sort of a consultant, but not much. I find it keeps me pretty busy at the medical school, trying to get the computers to do things with medical problems. I did pull a boner coming down here and mixed up the slides, and found that I had a set of slides on the respiratory properties or behavior of the turtle. And I've been trying to think of some way of introducing the mathematics of the airways of the turtle lung into this talk, but I couldn't do it. So
with the experience that you have, with the experience that you have and what you know of the state of the art today, where would you like to see us take it? Where would you like to see the path move?
At present, I'm just a user. I haven't done anything to aid computers for 35 years or so. Well, of course, you know that we can always use more memory. I'm losing my own, but I'd like to see the computer gain some. And we are finding the interaction with the laboratory, and I'm speaking now simply as a member of a laboratory organization, research organization that deals with the laboratory, easier ways of interfacing the computer and the laboratory. Ways are now available, and we're making use of them as far as possible. And I'm not sure just what could be done to improve the interfacing. It's fairly comfortable and convenient as it is, but I'm sure that if somebody comes up with bright ideas about improving that, they would certainly be acceptable.
Switching systems group on any of this? For example, the self-checking code sounds a lot like the 2 out of 5 code, which was subsequently used in switching. How did that information interchange work?
A number of the people I worked with, Sam Williams and Andrews, were from that kind of a background, and we did work with them. The self-checking code was not a completely new idea. The thing that was new about it was finding a code in which you could do self-checking and also do arithmetic operations. 2 out of 5, actually we did take a look at 2 out of 5, but all of the adding circuits that we could conceive of just got awfully messy and complicated. It just happened that there were several mixed binary decimal codes used in the telephone system, which the 2 out of 5 is one. But we couldn't find any that were adapted to arithmetic work. So that was the contribution on that, I think.
I'm just interested, you mentioned you're obviously having seen the Mark I. What relations, if any, did you have and at what time with Howard Aiken?
I'm counting on my memory here, and it's like all the others. My recollection is that we had completed the design of Model 1, and we're about halfway through with Model 2 when we heard there was something going on at MIT in the way of a computer. We did not have any real information about what was happening until 43, I guess, 1943. I don't know whether, I'm sure that that's true of anybody in the Bell Laboratories, because I would have heard about it. I'm sure that a lot of people knew that I was playing around with computers and relays, and if anyone had heard of work being done at MIT on a computer, they certainly would have let me know, I think. The communications was not very good.
The factor for preventing you essentially from having stored program. Was there much consideration of the trade-offs of stored program at that time, and did you get involved in some of the very early discussions?
No. We simply did not, at the prices that the bits were running then, we simply never seriously considered storing anything except the very simplest not a whole program, but simplest routines. We stored, for instance, the routine for division and multiplication and square root and a few things of that sort on relays, but that was all. Beyond that, to try to get even a few hundred words of program into a relay form would have been tremendously expensive. We didn't even try. I don't think we gave it very serious consideration because we knew we couldn't do it, and that was that.
I would have thought that the list-based types would have been sufficiently motivated to solve their problems in semi-real time to buy that stuff for you.
I'm sorry, in what? To do what? To solve?
To essentially say, go ahead and put in the memory if you can show us an order of magnitude improvement in speed.
Well, I don't think we could have. You see, we could do pretty well with the punch tape program because the operation of the rest of the system was pretty slow. And we did try to arrange the programs in such a way that calculations did not hold each other up. We had the independent table searching mechanism, which would operate by itself while the rest of the computer was off on its own business, and then they'd get together when the data was found. I don't think we would have speeded things up very much. We would have made it. We would have made the variety of problems solvable somewhat greater. That would be the main change, I think. Now, of course, if we were dealing with microseconds, then it would have been an entirely different matter. But the relays kept up with anything we could put into or the tape kept up with anything we could put into the relay.
How much in the way of data storage were in these machines? How many numbers could you store?
The complex number machine had 4 numbers. Let me see, I'm trying to find this. No, 4, I'm sorry, 4 real numbers. There were 5 numbers in the interpolator, but 2 or 3 of those were extremely short, of about 4 digits apiece, because they represented essentially high-order differences and therefore were not too much. The Model 3 and 4 had about 10 numbers, and Model 5, according to this record, has only 15. That, I think, must be an error, because we had a pretty complete set of calculators in 2 units, and each of those had a number of intermediate storages. But maybe the record may be right, but says 15, I say that.
Awareness of, during this period, Babbage and the other predecessors who you referred to at the very beginning of your talk?
Oddly enough, no. Not until we were 2/3 of the way through with the entire project. That is, until after Model 3 was made, I think. Somebody mentioned Babbage. Seems strange now. Everybody knows Babbage. Everybody knows binary notation. And it's hard to think back.
When you first heard about Babbage, did you investigate what he had done?
Not immediately. I was pretty busy at the time. We were working about, we seldom had less than 12 hours a day during the war. And after the war, I looked into it, yes. But then all the work was done.
What about Tories and some of those other?
I didn't hear about them until just within the last 10, 15 years. Should have. Looking back, I wish I had. But sorry.
When you were winding up, I guess the last model was the Model 4?
5.
Model 5.
Big one.
Why didn't you go on from there? What was the motivation for going on to something else?
The electronics was coming along. We did consider electronic actions, electronic computation before the design of Model 5 was started, but the pressure to get something reliable and predictable so that we knew when it would be finished was pretty heavy. And the relays are something that the telephone company handles by the tens of thousands. Everybody at every station in the telephone system, you can pick up a couple of people who are competent to wire relays. And that was not true of the electronics. And furthermore, the relay with its operational failure of 10 to the minus 11th looked pretty good compared with any of the vacuum tubes we could find. So we did not attempt to design anything with tubes. After that, they did come in, of course.
We have the same type of problems now.
Was any of the hardware you were working with stuff that had not been around in essentially the same form for 10 or 15 years?
Well, in the first model, remember they had the crossbar switches. They had only been in operation for 2 or 3 years. The rest of it was pretty old stuff. Oh, we had to do a little modification. We got the teletype company to arrange their tape reader so it would run either forward or backward, because we wanted to go through a table of ballistic data, and the computer would look at what it had and decide that this was too far to the left, and so it would run the tape off to the right for a while, and pretty soon it would get to the point where it had gone too far to the right and it went left one step. So it was very convenient to have a double-way action, and that I don't think has ever been standardized or used anywhere else. That was new. The rest of the stuff I think had all been in use for at least 10 years.
You said that the programming of the later machines was done in machine language, but you hinted at the use of abbreviations, which sounds like possibly the beginning of the assembler. Can you recall a little bit about how those abbreviations were converted to machine language?
Well, the abbreviation would actuate a relay. That is, the abbreviation represented a code to pull in a certain relay, and that relay in turn could do what you wanted it to, or 2 or 3 relays. Trying to think of a particular instance. It's been a long while since I went through these things. I think something about in the table hunting device, for example, you gave the machine an instruction to search for a particular number, and then a string of relays would interpret that to say go forward until such and such occurs, or go backward until that occurs. So it was the beginning of the language, but pretty simple.
The
I think it was the Model 5, could do jumps to various routines.
Right.
Was each of these routines stored on a separate reader?
Yes. Yes, they were stored on a separate. See, since all the problems that we dealt with had a great deal of cyclical behavior, the tapes, the program tapes were almost always, I shouldn't say always, almost always punched and put into a loop. And so to jump, rather than go back through a tape which carried the jump in it, when you reached a jump, you went to another reader, and you followed that routine until you wanted to come back. We could, I think originally we thought of putting the jumps in the same tape, but the time involved in hunting through the tape until you found the place to jump to was pretty serious, and so it was easy to jump to another tape entirely.
Was there a focus on performance? It looks like you're really working on reliability most of the time, and were you out to make higher performance machines? I know you gave this comment about ENIAC.
No. Well, we wanted to push the performance as high as we could without modifying design principles too much. And, well, we tried to get the fastest relays, and we tried to arrange circuits. We did at one time. I have a sketch back at the school which shows the use of gas tubes to speed up some of the operations, and in that way we did try to push it, but as compared with reliability, we just didn't care.
What was the operations rate of the Mark V, say, compared to the one?
Oh, let me see. Multiplication time, 5-digit numbers, 0.8 of a second. It says five-digit number, which I don't understand. I think that must be an error because it was a 7-digit machine. So I don't think maybe they were sort of picking an average size. I don't know.
Were any of the British computer pioneers in particular, did Turing visit you during the war?
Yeah, Turing visited the laboratories, but he was not interested in the computer. He never talked to me about it. He was interested at the time in cryptanalysis, and he talked entirely to Claude Shannon. The two of them formed a little group, and I don't think anybody else got a chance to talk to Turing at all, which of course I regret because he was a great person. I explained to him one time, somebody said maybe Dr. Turing would be interested in what you're doing, and I gave him a brief rundown on what we were doing. But as far as I can recall, he didn't say a word. He didn't ask a question. He didn't say a thing about it. He was under pretty severe, strict secrecy conditions at the time. He may have been overstepping the requirements, but I guess he was playing safe. We had a sort of a cryptanalysis device too called Madam X, which I don't know if it's still classified or not, but it has been for so long. That was a relay device. After we got the Model 1 working, John Friedman from the secret from the cryptanalytic group came up and talked to us and wondered whether something could be done to simulate the German device at high speed with relays. And we told him we thought it could. He and Sam Williams and others got together and built quite a large machine called Madam X, which did that sort of work. I hope it isn't still classified. I don't know. I may be shot on my way out. The talk will be over by then.
What type of power consumption do these machines have?
it's not, I think the Model 5, the big one with 9,000 relays, must have used a kilowatt or so. That's not given in my data sheet. The relays around 2,000 ohms, and about maybe 10% of them are operated at any one time. So maybe you got 1,000 relays, 50 volts, 2,000 ohms. You've got a calculator there. Maybe you can do it faster than I. But it's not over a kilowatt, I'm pretty sure.
Do you remember what the typical switching time for those relays was?
We had a number of different designs of relays, different windings particularly, for different purposes. 10 milliseconds, I think, was the fastest that we had, and we used them in the adding circuits. 10 milliseconds operate time, and that got our contacts made, and the release time was less important because we transferred that number elsewhere. So we used relays that were fast operating in some circumstances and fast releasing in others. And that part of the work was largely the contribution of the relay circuit people. They were very good about that, picking the relays that would do the fastest job.
I think we ought to adjourn to the wine.